Hello friends, welcome back to my YouTube channel. Today I will continue my discussion on high pressure vessels and then the theories of elastic failure. And in this particular video, I'll be talking about the maximum strain theory. In my previous videos, I had discussed maximum principal stress theory and then maximum shear stress theory. I'm giving link to those videos in the description section. Those of you who have not yet seen those videos, you please watch those videos. So today the objective is to discuss maximum strain theory. So this theory accounts for elastic failure in materials. So let us begin the discussion. So why we are understanding these theories? Because the design of high pressure vessels, it is based on in the theories of elastic failure. So whenever high pressure vessels are designed, their design is based on the theories of elastic failure. As far as elastic failure in a material is concerned, it is going to occur when the material is subjected to a load that exceeds its elastic limit. So elastic limit is a point till which the material will be behaving elastically. That is, if a load is applied to a material and it will be deformed, there will be change in its shape and size, but within the elastic limit, if the load is removed, the material regains its original shape and size. So elastic failure, it occurs when the material is subjected to a load that exceeds its elastic limit. Beyond its elastic limit, what happens? The material gets permanently deformed, or you can say permanently ruptured. So beyond once the elastic limit is crossed, the material is going to get permanently deformed. So many theories have been proposed to account for this elastic failure, to account for the elastic failure in material, and these theories, we call them the theories of elastic failure. What are important theories of elastic failure? You have maximum principal stress theory. I have already discussed it. Then you have maximum shear stress theory. I have discussed it. And today I'll be talking about the maximum strain theory. And in my coming video, I'll be talking about the maximum strain energy theory. So the objective for today is to discuss the maximum strain theory to account for elastic failure in materials. Okay. Now, what is this maximum strain theory? According to this theory, failure in a material will occur if the strain set up in the material becomes equal to the strain at the elastic limit. And this elastic limit is taken as the yield point of the material. So what does the maximum strain theory suggest? The theory suggests that a material is going to fail if the strain set up in the material, it becomes equal to the strain at its elastic limit. And the elastic limit in this case, it is taken as the yield point of the material. So yield point is that point beyond which the material behaves plastically or material deforms plastically. Material is not able to regain its size and shape even when the load is removed. Okay. So the limiting strain that is considered in this theory is the maximum. Let us understand what is the limiting strain that is to be considered, or that is considered in this theory. For that, the first thing that we know is the maximum principal stress is the circumferential stress. We have understood this earlier. The maximum principal stress is the circumferential stress, and that too at the inner surface of a cylindrical vessel. So if you talk about a cylindrical vessel, then the maximum principal stress that is induced in the wall of that cylindrical vessel is the circumferential stress at the inner surface, and I denote it by sigma CR. Therefore, the limiting strain that is to be considered is given by this equation. Again, we are directly taking this equation in our discussion. We are not, I'm not discussing the derivation. So the limiting strain that has to be considered, or that is considered, is epsilon C is equal to 1 upon E into sigma C minus mu into sigma R, where in this equation, E is the modulus of elasticity, sigma C is the circumferential stress, sigma R is the radial stress, mu is the Poisson's ratio, and that equation, or the equation, will give us the strain, the limiting strain that is considered in this theory. So the limiting strain to consider is epsilon C is equal to 1 upon E into sigma C minus mu into sigma R. And we are going to consider this at the inner surface. That means when D is equal to the inner diameter of the cylindrical shell, and when P0, that is external pressure, is 0. Why P0 is 0, PO is 0? Because in most of the high pressure vessels, the external pressure is considered to be 0, or the external pressure is 0. So sigma C is given by this equation. I have derived this equation in my earlier discussion on high pressure vessels. You please watch those videos. So sigma C is pi di square minus po do square upon do square minus di square plus do square into di square upon d square into pi minus p naught upon do square minus di square, where pi is the internal pressure, di is the internal diameter of the cylindrical cell, po is the external pressure, and do is the outer diameter of the cylindrical shell. Taken. Then sigma R is given by this equation. Pi di square minus po do square upon do square minus di square minus do square into di square upon d square into pi minus p naught divided by do square minus di square. Again, this equation is considered along with the sign convention. What is the sign convention? The compressive stress is negative, and in this case sigma R, the radial stress, is negative. So I have considered this sign convention while writing this equation. So if you use these conditions, that is at the inner surface and when external pressure is 0, the equations will be modified in this way. So sigma C is equal to pi di square minus PO is 0, so 0 into do square upon do square minus di square plus do square into di square divided by di square, that is now d is replaced with di into pi minus 0 because p0 is 0 divided by do square minus di square. That is sigma C is equal to pi di square upon do square minus di square plus do square into pi upon do square minus di square. So di square get cancelled. This term is 0. This is 0. So the equation modifies to this form. Sigma C is equal to pi di square upon do square minus di square plus do square into pi upon do square minus di square. So in the next step, what can be done? Pi upon do square minus di square. It is a common term that is present in both the terms. So you can take that as common, but we'll do that afterwards. Now let us look at the equation for sigma r. So sigma r will be pi di square minus po0. So minus 0 into do square upon do square minus di square minus do square into di square upon di square, where d again we are replacing with di into p minus po. Po is 0 upon do square minus di square. That is sigma r is equal to pi di square upon do square minus di square minus do square into pi upon do square minus di square. Okay. So equations for sigma c and sigma r, they are transformed to different forms by using these two conditions. At the inner surface, d is equal to di, and the external pressure, that is P0, is 0. So with this, equation for epsilon c will now be written in this way. Epsilon c is equal to 1 upon E into pi di square upon do square minus di square plus do square into pi upon do square minus di square minus mu into pi di square upon do square minus di square minus do square into pi upon do square minus di square. So I have simply used equations for sigma c and sigma r in the equation for epsilon c. Okay, now let us move ahead. Again, the limiting strain now is this. After using the equations for sigma c and sigma r, epsilon c is equal to 1 upon E into pi di square upon do square minus di square plus do square into pi upon do square minus di square minus mu into pi into di square upon do square minus di square minus do square into pi upon do square minus di square. So now let us simplify. What will be the simplification? Let us see. Now I'm multiplying the two terms with mu for this particular bracket. So this will be epsilon c is equal to 1 upon E pi di square upon do square minus di square plus do square into pi upon do square minus di square minus mu into pi di square upon do square minus di square plus minus becomes plus, so plus mu into do square into pi upon do square minus di square. So in the next step, what we will do? Epsilon c is equal to 1 upon E. That is 1 minus mu. That means if you look at this term and then this term, so pi di square upon do square minus di square is common. So that is taken out as a common term. So it will be 1 minus mu into pi di square upon do square minus di square plus again from the other two terms, that is do square pi upon do square minus di square plus mu into do square into pi upon do square minus di square. Do square into pi upon do square minus di square is a common term, and that is taken out. So you have plus 1 plus mu into do square up into pi divided by do square minus di square. So if you simplify this further, it will be written in this way. That is, again you can take pi common. So you have epsilon c is equal to pi upon E into 1 minus mu di square upon do square minus di square plus 1 plus mu into do square upon do square minus di square. Further, this will be simplified. The denominator is same for the two terms. So you can write it in this way. So epsilon c is equal to pi upon E into 1 minus mu di square plus 1 plus mu do square divided by do square minus di square. Okay, so now let us continue with the equation that we got at the end. So you have the strain at the elastic limit. That is, we are considering the strain at the yield point. Okay, so we got equation for the strain, the limiting strain to consider. That is to be considered, or that is considered in this theory. Now let us talk about the strain at the elastic limit. That is, we are talking about the strain at the yield point. And at the yield point, stress and strain, they are related by this equation. Sigma y is equal to E into epsilon y. Sigma y is the yield stress, E is the modulus of elasticity, and epsilon y is the yield strain, the strain at the yield point or the strain at the elastic limit. So according to the theory, as per the theory suggests that the strain set up in the material or the strain induced in the material is equal to the strain that would be set up and at the yield point. So epsilon c is equal to epsilon y. For epsilon c we got the equation. What was that equation? Epsilon c is equal to pi upon E into 1 minus mu di square plus 1 plus mu into do square upon do square minus di square. And from this equation you can get equation for epsilon y. Epsilon y will be equal to sigma y upon E, that is sigma y upon E. Now let us follow the theory. Let us equate these two straits. So it will be pi upon E into 1 minus mu di square plus 1 plus mu do square divided by do square minus di square, that is equal to sigma y upon E. Now E will get cancelled. You have modulus of elasticity on both the sides, so that will get cancelled. So you'll have pi into 1 minus mu di square plus 1 plus mu do square divided by do square minus di square, that is equal to sigma y. That is sigma y is equal to pi into 1 minus mu di square plus 1 plus mu do square divided by do square minus di square. I have just rewritten the equation in a different form. Okay. So over here we have got equation for sigma y, that is the stress at the yield point. And this will be used or this will be the yield stress according to the maximum strain theory, or you can say this equation is the equation according to the maximum strain theory. Now let us simplify it. So this is the condition at which failure is going to occur according to the maximum strain theory. Okay. Now let us convert this into a design equation. So how that is to be done, let us understand. So according to this theory, we just got this equation for sigma y. Sigma y is equal to pi into 1 minus mu di square plus 1 plus mu do square divided by do square minus di square. And let us get the design equation. For that, for the design purpose, we are going to consider a factor of safety, Fs. Why we are going to do that? So that the induced stress will be less than the yield stress. That is, we are going to use a lower value for sigma y. Okay, so for design purpose, a factor of safety, Fs, is used so that the induced stress will be less than sigma y. So how to use this in the equation? It will be sigma y divided by Fs. So we are going to divide sigma y by Fs, the factor of safety. So therefore sigma y upon Fs is equal to pi into 1 minus mu di square plus 1 plus mu do square divided by do square minus di square. So if you simplify it further, how we are going to take di squared, or we are going to divide the numerator and denominator with di square. So if you do that, it will be sigma y upon Fs is equal to pi into 1 minus mu di square upon di square plus 1 plus mu into do square upon di square divided by do square upon di square minus di square upon di square. So in the next step, di square upon di square will become 1 and do upon di will be replaced with k, the ratio of outer diameter to inner diameter. We are going to replace that with k, and if we do that, it will be sigma y upon Fs is equal to pi into 1 minus mu plus 1 plus mu k square divided by k square minus 1. And you must have noticed we have replaced do upon di, the ratio of outer diameter to inner diameter, with k. Okay, so that gives us sigma y upon fs into k square. Further simplification, sigma y upon fs into k square minus 1, that is k square minus 1. This term I have brought on the left hand side, so it will be sigma y upon fs into k square minus 1, that is equal to pi into 1 minus mu plus 1 plus mu k square. That is sigma y upon fs into k square minus sigma y upon fs. I am multiplying sigma y upon fs to each of the term in the bracket. So you have sigma y upon fs into k square minus sigma y upon fs, that is equal to pi into 1 minus mu plus pi into 1 plus mu into k square. That is sigma y upon fs into k square minus pi into 1 plus mu k square, that is k. I have collected k square terms containing k square on the left hand side. So that is sigma y upon fs into k square minus pi into 1 plus mu k square, that is equal to pi into 1 minus mu, and this term I have taken to the right side. So it will be pi into 1 minus mu plus sigma y upon fs. Now let us continue with this, the equation that we, so the design equation, we got this sigma y upon fs into k square minus pi into 1 plus mu k square, that is equal to pi into 1 minus mu plus sigma y upon fs. So what can be done in the next step? You can take k square common on the left hand side. So it will be sigma y upon fs minus p into 1 plus mu into k square is equal to pi into 1 minus mu plus sigma y upon fs. And in the next step, this term will be brought on this side. So it will be k square is equal to sigma y upon fs plus pi into 1 minus mu, this term written in a different form, divided by sigma y upon fs minus pi into 1 plus mu. So we can simplify it further. Therefore, k square is equal to sigma y plus pi into 1 minus mu into fs upon fs divided by sigma y minus pi into 1 plus mu into fs upon fs. So in the next step, fs is going to get cancelled out and you are left with k square is equal to sigma y plus pi into 1 minus mu into fs divided by sigma y minus pi into 1 plus mu into fs. That is k is equal to sigma y plus pi into 1 minus mu into fs divided by sigma y minus pi into 1 plus mu into fs raised to 1 by 2. And this equation, you can call this as the design equation as per shear maximum strain theory. So sigma y, pi, mu, fs will be known to you. The only job that you have to do is find the value of k. And once k is calculated, you can get information on the inner and the outer diameter. In this case, internal diameter may be provided to you, and then you have to calculate the outer diameter. And from outer diameter and inner diameter, you can calculate thickness of the vessel, because the outer diameter is equal to inner diameter plus 2 times of thickness. So if you look at the vessel from the top, let me just show you. So you have the inner diameter, then you have the outer diameter, and this is the thickness of the vessel, ts. Sorry, this is inner diameter, and this is again the thickness. So do is ts plus di plus ts. So that is do is di plus 2 times of the thickness. So k, value of k will be used to find out the outer diameter, and then outer diameter and inner diameter will be used to find out the thickness according to this equation. Okay. So with this, I end my discussion on maximum strain theory. We have understood what is the theory, how elastic failure occurs in the material according to maximum strain theory, and then finally we have got this design equation that will that can be used to calculate thickness of the high pressure vessel. Okay, so I hope you have understood the concept. If you have any doubt, mention them in the comment section. Thanks for watching my video. Do subscribe to my channel. Hit the bell icon so that you'll be notified as soon as I upload any new video on my YouTube channel. And have a nice day. Hope to see you soon in my next video, where I'll be discussing the fourth theory of elastic failure, that is maximum strain energy theory. For now, bye bye. Have a nice day.